Cohort B, okay, and Cohort A for tomorrow, actually. So, guys, just a short lesson today. I just wanted to tell you about another kind of diagram. Listen, yesterday we talked about the Lewis dot diagrams, okay, and how to draw those. I'm just going to pick one of the elements here. I'm going to pick magnesium, so it's 12 and 24, okay, the atomic number, atomic mass. Okay, and then I'm just going to show you how you draw a different kind of diagram with this. So, magnesium, okay, has an atomic number of 12, an atomic mass of 24. Okay, so I'll put that a little card here. So, therefore, you have 12 protons, 12 electrons, and 12 neutrons. Okay. How did I get 12 neutrons? Well, here I'll show you. The number of neutrons will equal 24 minus 12, which also happens to be 12. So it's all coming up 12s, right? All right, so let's draw the diagram. I have 12 protons. I have 12 neutrons in the nucleus. My first shell holds 2 electrons. My second shell will hold 10 more. Sorry, we'll hold 8 more, pardon me. Okay, and then my third shell, for a total of 10 is what I meant to say. My third shell, magnesium has 2 electrons left. Now, normally we sort of pair these together. Okay, that's magnesium. Okay, so I just want to point out to you that the valence shell has just 2 electrons in it. Okay, and I've been talking about the valence shell to you. I mentioned this to both cohorts now. It's how many valence electrons you have. So valence is the outer shell. It's that outer shell that determines your physical and chemical properties. Okay, so what gives each element their own unique character has to do with how many electrons are in that outer shell. All right, so that's kind of the key point. So sometimes to get to the point, this is pretty time consuming to draw that diagram. And I know the textbook asks you to draw several just for practice. Yeah, I mean, as long as you can do it, I mean, on the next quiz or test or whatever, we'll definitely be drawing these. You'll have a periodic table when you do that. Okay. But anyway, there's a simpler kind of diagram called the dot diagram. So dot diagrams, what they're made for is showing, the valence shell only. Okay? So since the valence shell is the most relevant shell, why don't we just show it that way? So let me show you how you do it for magnesium, and by showing you how to do one of them, I think you'll see how it works. It's pretty straightforward. Okay, so the way we draw magnesium is you just draw the symbol. Okay, so the symbol for magnesium is Mg, and then it has 2 valence electrons, so I just draw the 2 dots like that. Now I just want to point out that the valence, there is a rule for where we place the valence electrons. Since you can have up to 8 in the first, we'll only do the ones for the first 3 rows, okay, the elements in the first 3 rows. Since they only go up to 8 electrons, then I'll show you how you might place it, like say neon. Okay, so here I'll put a couple of examples. Neon has a full outer shell. Okay, it's one of the noble gases. It has 8 electrons in its outer shell. So you put them, imagine an imaginary box that surrounds the element name. You put the electrons, let me just fix it. You put the electrons on the 4 sides of that box. Okay? So neon has 8 valence electrons, and that's what it looks like. Now actually you can tell by how many valence electrons the atom has just by looking at what column it belongs to in the first 3 rows. So for example, if you're an alkali metal, in the first column you have 1 valence electron. So if I wanted to draw sodium, sodium is an alkali metal, it has one valence electron, I would just draw it right there. Now it really doesn't matter what side you put that valence electron on, but just put it on one of the four sides of your imaginary box. Fluorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and then 7, like that. Okay, notice how they're paired up. So if you look at the periodic table again, let's just go back to that. If you look at the periodic table, we can pick any element here we want, okay, and sort of just draw. Here, let me do it here like this. I'm going to get rid of these highlight marks that I made. Okay, so let's say you wanted to do boron. Well, boron has 3 valence electrons. And so to do boron, actually I'm going to zoom in a little. If I wanted to draw boron, I could just put the dots right next to boron, right? It has 3, so I put 2 on one side, and then the single guy on another side, okay? Carbon's kind of unique. Sometimes we don't pair them up. We can go 1, 2, 3, 4 around carbon, because sometimes it actually is that way, okay? Nitrogen has 5, right? So you could go 1, 2, 3, 4. Well, actually, you know what? This looks terrible. I'm going to do it again on a separate page. So let's do nitrogen back on this page here. If I wanted to do nitrogen, it has 5 valence electrons, and I can tell immediately. I don't need to draw the Rutherford-Bohr diagram. I can tell just by what column it's in that it has 5, right? So I could go like this: 1, 2, 3, 4, and then 5, like that. So I tell you to always pair them up, but sometimes they're not paired up, okay? It depends, okay? Especially, usually 2 of them pair up, and then sometimes the other ones are individual. But you do want to put them, like I said, in that imaginary box, on the sides of the imaginary box that surrounds the element. That's how you draw the dots. Please don't draw them in a circle, okay, around it. It's like a square. Helium has 2. You just draw it like that. Okay, argon. Let's see where argon is. I think it's on the 3rd row, but I just want to make sure. So argon would be, yes, argon would have 8. So let's go with argon. Argon has a full outer shell, so you would go AR for argon. Just fill it right up. That is the configuration of argon. Okay, so does this make sense? Chlorine, by the way, if I were to draw chlorine, I'll draw it here next to fluorine. Chlorine also has 7 valence electrons. It is in the same group as fluorine. It's a halogen. It's in the same column. And it has similar properties for that reason, because it has the same number of valence electrons. See how similar those diagrams are? I guess I could do it like just to be consistent. I'll put that last dot there. So those are called dot diagrams. And here it shows the valence electrons only. Okay? So it shows you how many valence electrons each element has. Okay, so this is a very important kind of diagram. They're used all the time later on. We don't like drawing the Rutherford-Bohr. It's kind of tedious to draw the protons and neutrons and stuff. After all, the chemical properties, if you're talking about chemistry, depends on those valence electrons. Not so much on the number of protons in the nucleus, although they play a role. It's the valence electrons that determine what family you're in. Okay? And what family you're in is all about your chemical and physical properties. All right, so that's how you draw dot diagrams. Now, I will say this. We're going to talk about this later on, but I'm going to mention it to you now. There's something called the octet rule. Now, octet means 8. Okay? So, what atoms like to do they like to have full valence shells if they're nonmetals. Okay? And the reason why they like that is because it makes them more stable. So they kind of naturally seek this out. So for example, if you're fluorine, okay, I'll draw it again for you. Fluorine looks like this, okay, symbol F. It almost has a full shell, and here I'm going to put a little X in here. It's missing just one, okay, electron. And fluorine is an amazing thief. It'll take electrons from something else. Like it wants to fill that electron, that empty spot, more than any other element on the periodic table. It wants an electron more than any other element on the periodic table. Okay, we have a word for this in chemistry. It's called electronegativity. How attractive are you to electrons? So for atoms on the periodic table, the most attractive element is fluorine. Okay? In other words, electrons are drawn to it, and fluorine can steal electrons from almost anyone, with the exception of the noble gases. The noble gases are so happy to have the full shell. They're happy because their shell is full, and since nonmetals, that's what they want, is have the full shell. You can't take one from the noble gas. That will make it more unstable. Okay? And so atoms will not do that. And so you cannot steal from a noble gas, but you can steal from, fluorine can steal from almost anybody else. Okay, it is the most electronegative element, the most attractive element to electrons. Okay, so this is very attractive to electrons. Okay, to fill missing spot. And once it fills the missing spot, fluorine will have 8 electrons, okay, and it'll have a perfect octet. You get it? We call it the octet rule. That's what nonmetals want. Okay, they want to have 8 electrons. The only exception is hydrogen. Hydrogen only needs 1 electron, so I'll say this, the exception. And hydrogen is kind of an exceptional element just because it's in the first row and it doesn't have a full shell. Hydrogen has 1, but the first shell only holds up to 2. So it's not an octet for hydrogen. It has 1 empty spot there. Okay, so hydrogen is very reactive, just like fluorine. Not as much as fluorine is though, but it's still a pretty reactive element, hydrogen. It would like to have 1 more electron. Kind of like fluorine, but just not, it's not as strong as fluorine is, okay? So here would also like 1 more electron, but this time not 8 to fill the shell. Okay? Now, metals are very different. Metals don't have enough electrons, and it's too hard for them. Like for example, if you're sodium, sodium has 1 valence electron. Let's say you're sodium, you're an alkali metal. Well, it's going to be next to impossible for sodium to get 7 more electrons to fill in its empty spots. It's way easier for sodium to just get rid of 1 electron and see the shell underneath is full. Right? So what sodium does is it gets rid of its valence shell, and then the shell underneath the valence shell becomes the new valence shell, which is already full. Okay? So these get rid, they will lose, I should say, valence electrons. In this case, just 1. To expose the full shell beneath. See, that's what makes metals metals. Metals are metals because they have a weak hold. Okay? They have a weak hold on the valence electrons. And that weak hold means they're good conductors of electricity. Electrons move easily around the metal atoms because their hold is weak. Okay, if that makes sense to you. They want to get rid of them. Okay, and that's what makes them good conductors of heat and electricity. Okay, now I have something for you. I want to keep this lesson short today. I have something for you to read. So, by the way, metals like sodium will get rid of one electron. If you're magnesium, we already did that, that has two, it'll get rid of both of those. It can't just get rid of one, it has to get rid of both. It's all or nothing. Okay? Because if magnesium were to get rid of just one electron, it would actually be more unstable like that. They need to become more stable. It's the only reason they do this. So for magnesium to become more stable, it must lose both. Okay? All right, so I have a reading assignment for you. What I did here in these 2 pages is I defined what a chemical property is. I'd like you to read this. Okay? So what are chemical properties? The note is pretty clear, but I'd like you to read it. I also wrote down some physical and chemical properties of most of the groups on the periodic table. I would like you to read that too. Okay? Just read it over, and then we'll talk more about it after your test. So that's it for today, guys. Okay? So I have some pretty light reading. Okay? You have a test tomorrow, so I wanted to keep it light for today. There's a little bit of homework. So if you look in the outline, all we did today, okay, the dot diagrams, we didn't do, this homework is here. If you don't want to worry about it until tomorrow night, that's fine with me. Okay? All right, guys, so have a good day, and we'll talk to you soon.